Hello.
Hi.
Who's that?
Oh, that's Ariel from Tees.
Oh, hi, Ariel. How's it going?
Yeah. I think you might have not met Ariel, but Ariel has been helping Nicole for the past
okay,
over the past one.
I know Nicole really well. Yeah, that's why. So when I heard her voice, I mean, I thought it was you. I was like, all right, okie dokie.
So, Raj, we're still in practice mode since I gave you the host.
Right.
Here in about a minute, you'll just need to click that button that says start.
Raj, I can't see you.
Yeah, I didn't turn on my camera yet.
Okay.
Yeah.
It's a surprise.
All right. There you go. Yeah. Still photo.
So yes, I am able to cast the live, and I will share the link just between us,
Okay.
host and panelists. So if you guys can verify if you guys can see the live
In the chat room.
So I sent you the link.
Yeah, I see it.
I sent you the link in the chat box. But I will share the link just between us, host and panelists. So if you guys can verify if you guys can see the live
in the chat room.
So I sent you the link.
Yeah, I see it.
I sent you the link in the chat box.
All good.
So now, yeah, I don't know if I can pause it. Yeah, I wish I had a way to pause it. But anyway, so for now, I'm going to open the banner or the poster for the conference or for the webinar, and then I'll leave a shared screen with that picture.
That's good. Yes.
Okay. All right. So you should be able to see the poster now.
I see the poster in the webinar. I don't see it yet in the live stream, but it's about a minute delayed.
Right.
There it goes. Perfect. So I can see it on the YouTube. I'm going to go ahead and mute myself now. I'll be here. Just when you're ready, it is a little after 7:30. If you want, go ahead and press that start. So we go out of practice mode and then it'll start recording.
So the hosts and panelists should be able to join. Sorry, go ahead, Prakash.
Yeah, sorry, Raj. I think Ariel's her microphone is a bit, it's the start off. Yeah, I mean, it's a bit, it's not seamless.
Yeah, I think maybe there might have been a little bit echo where she was playing the live video in the background, so there might have been some echo there.
No, even now, Raj, I mean, like it's not seamless. Yeah, even audio to me at least. Yeah.
It sounded okay to me. and even your audio is coming out pretty clear. So
Yeah, so that's odd. Yours is not seamless, yeah?
Yeah.
Well, I'll be muted, so you don't have to worry about my audio.
No, I'll be likewise
No,
muted.
I'm just concerned about my, because both of y'all, are intermittent, yeah?
Yeah. So essentially, Ariel, there will be only 3 people talking, Dr. Prakash and Dr. JN Reddy and the speaker, Dr. Yonggang Huang. So those will be the only 3 people that will be talking. So don't have to much worry about the other speakers being able to talk. So that will be.
Hey, Raj, I thought maybe for the Q&A, like maybe I could call up on people to talk, ask. If they don't, then I can ask them a question. I can ask them
Sure.
a question.
Sure.
Yeah?
Yep. Okay.
Isn't Arun joining us?
He should be able to. I think panelists and hosts should be able to join anytime. It will be just for the public audience. They'll not be able to join until we
at 8 a.m. right?
Yeah.
I mean, whenever we start webinar, they should be able to join. But I mean, it's just up to us whether we want to start it right away or like maybe 15 minutes before 8. Yeah, 7:45.
Just give me a cue, by chat or something, Raj, or even like a WhatsApp, like when to start. Yeah.
Sure.
I mean the proceedings. Yeah.
Yep. Absolutely.
It's Arun.
Yeah, there's Dr. Srinivasa. Good morning, sir. Dr. Srinivasa, you're muted.
Yeah, there's some slight echo.
Is it?
Yeah.
Yeah, so it's hi Prakash, how are you? Good morning.
Hey man, how's it going?
So you are the master of ceremonies.
Yeah.
Good.
Apparently.
Yeah, no, I mean you really did a good job. So it's good. So Raj, it looks like if you're muted, it's okay, man. So somehow we're getting some feedback from you, Raj.
Yeah, that's the thing. Even for me too, there's some feedback. It's very bizarre.
Yeah, slightly.
Yeah, I was muted until a second ago.
Yeah, there's some. It's really odd. I mean, something. Yeah, it's from your side, Raj, for sure.
Okay.
Something.
I'll be anyhow muted, so I don't think it would really matter. So.
Yeah, I think it's okay. So JN is
Arun, when I'm speaking, is it clear or is it intermittent?
Little bit breakup. It's not completely 100% clear.
I mean, if you have a few more minutes, you can leave and come back and see if something as simple as that would fix the issue.
Yeah.
Shall I do that?
Yeah, just
leave, and I think it'll make me host automatically again, and then I'll remake you host.
Yes, okay. Thank you.
Okay, I'll leave, yeah. Hey guys.
Yeah.
Hi.
Hi, how are you? Yeah, just speak up a little bit to Prakash and see.
Yeah, no, I mean, when you're speaking up as well, it's breaking. It's intermittent.
Yeah, there is some slight delay between video and sound. That's what it is. It's okay. We're also live streaming it to a YouTube thing, Raj.
Sorry, Dr. Srinivasa, can you repeat that again?
Yeah, I was going to say we are live streaming it to a YouTube.
Yes, that is correct, sir.
Yeah, very good. That may be. Yeah, I mean that's.
I posted the YouTube link. I mean, reposted the YouTube link at least just for our organizer team in the chat box. Can you?
Yeah.
Okay. All right. Awesome.
Yeah, you have to send the link again because we went out and came in back here.
I don't have anything on my chat box.
Yeah, because you came later after he. There you go.
Yeah. Yes. Okay. Yeah, both of them showed up now. Yeah, it's the streaming is working.
Thanks for the confirmation, Dr. Srinivasa. All right, I'm going to start the webinar so that the people can join now.
Yes, okay.
Good morning, Dr. Huang.
Oh, good morning. Good morning.
Good morning, Dr. Huang. How are you?
Hi. Hi, Arun. How are you?
Pretty good, pretty good. Good to see you.
Nice to see you. Thank you.
Yeah.
Yeah, I hope you were able to comfortably log into Zoom and connect.
Yeah.
Hi, Dr. Huang. Good morning.
Good morning. Good morning.
It's morning in Malaysia. That's why, hence my good morning.
What time is it in Malaysia, Prakash?
It's 8:45 in the evening.
Evening, yeah. So we picked a time that will be reasonably okay for a vast majority of the world. So that's why it's kind of early in the morning out here.
No worries. I mean, the only winners here are always Europe, sir.
I know. So we should probably ping JN just in case.
Yeah.
He just had cataract surgery, so he's been little bit, he had both eyes. So it's been a little bit.
Just a quick question.
Yes, sir.
Right now, I try to share screen and said I'm not allowed to share screen yet.
Yeah, I just updated the right, so you should be able to share now.
Okay.
Yeah, so you should.
Can I try it? I just want to try
Yeah,
to make
Yes,
it.
go ahead.
You can try. Yeah.
Please do. Please do.
Yeah, we can see your screen.
Yeah, let me call JN just in case. Maybe he's having trouble
Okay,
with
great.
logging in something. So let me just call him.
Okay.
The recording has stopped.
Okay.
Awesome.
I have stopped the screen share, right?
Yes, you did. You did.
Yes.
Good morning, Yang. Can you hear me?
Yes. Good morning, JN.
Good.
Hey, JN, how are you?
Good. I was speaking with mute button on. Okay, so very good. So it's all right. We are all set, right?
Yes.
Yeah.
So I think we are still 7 minutes.
Yeah, we can start
and-
on the dot, yeah?
Yeah.
Just give me the get-go.
And Raj, we stopped recording.
I think so.
Yeah, I stopped recording. I just wanted to start at 8 when we start the
Yeah,
event so
right.
that we
Very
have
good.
a perfect recording.
Yeah, very good.
And I don't have to go ahead, Dr. Reddy.
First, let me introduce the team here to
Yeah,
Yang.
sure.
Yeah. Yang, you probably did not meet Prakash. So Prakash, raise your hand. Where are you? Are hiding?
Yeah,
Who,
I
me?
saw him. Yeah.
No, we are seeing him, Dr. Reddy.
Okay. So Prakash was a former student of Lalit Anand at MIT.
Oh, very nice.
Right. Then he was a faculty member at NUS when I was visiting there.
Okay.
So that's where I met him. So
Very nice.
So then he's Indian origin but Malaysian. He was born
okay.
in Malaysia. Okay. So he went back to be a professor at the National University of Malaysia, which has a specific name. So he has been collaborating with us on graphia related, in general, on fracture. Okay, so we have done, as you have listened to me a couple of times, very good work. So I just want to know him, and of course, you know Professor Arun Srinivasa, right?
Of course.
Arun is a central piece in this research, and more importantly, he works with me in all kinds of things, including this JN Reddy medal.
Yes.
Very nice.
In
Very
the
nice.
background.
Thank you.
Yeah, in the background. So, I'm sorry that I did not put him up front, but in the beginning, but
No. I mean,
right. So then Dr. Kota is a research engineer. Is that right title?
Yes, that is correct. Yes.
Works with the Army Futures Command. They have BCDC. I don't know exact expansion of it, but
Bush Combat Development Center.
It's complex. Yeah.
Complex, sorry. Bush Combat Development Complex.
Yes.
Very nice.
That itself is a
complicated one, but so in the background, without taking too much time, so AFC gave a good amount of money, something in the ballpark of 65 million for 10 years.
Mhm.
So I don't know where that money going, but so Arun and I are part of that, but we don't get any money there. So I think so we are trying to get out of that obligation and independently work with the Army with regard to graphia. So anyway, that's the background. So Prakash will host this whole thing. He is the person
Master of the ceremony.
Master of ceremonies, yes.
Okay, master of the ceremony. So he will kind of, smoothly get into the flow by asking you a few questions. Nothing out of ordinary, just to
don't worry.
the warm-up session, right? Yeah. So making
to break the ice.
So we have done that before, whether you watched it or not when Glausio received it. So, okay, any questions, Yang?
No, it's just a pleasure to meet the team. It's really a pleasure.
Yeah, that's. So I wanted you to know them because it should not be strange.
Sure.
Okay.
And it's an honor to host you and have the chance to talk to you a little bit. In fact, Prakash has always does a very good job in terms of asking questions related to how you got into research and all this stuff. Because we're also trying to get young people thinking about how people like you, how you proceed with your, how you got to where you are. So it's always a good thing for people to
provide something like your.
That's really the best question. I mean, JN is the best, can give the best answer.
Oh yeah, we already did that. So with JN, we already did that. So we are slowly, we did that with Glausio, and then JN, we had a very extensive one. And anyway, his over time we will have many more options. I mean, opportunities with JN. So things are coming up. So so that's the other major item.
Okay, so we are 2 minutes away from starting. So I'm going to start recording now, and then we can maybe wait for a couple of minutes and start the event.
So is there a count that I can see somewhere?
Yes, if you click on participants on the top, then you should be able to see 6 panelists, and then there are 16 attendees as of now. And then there are 5 people watching us on YouTube.
Yeah. So it will get, people will log in now. So in the next probably 5 minutes, people will log in. It usually takes a little bit of time.
So Yang, we are recording, so it would be put on YouTube.
Oh, okay. Thank you.
Yeah, because it would be, we want people who could not attend to have the opportunity to watch.
Hear your talk.
Yeah.
Yeah. So this is part of the CiMDM channel, right? Right.
Yes.
Yeah. So this is part of our center's YouTube channel. So it will be recorded as part of that channel.
Great. Thank you.
Yeah. So we'll send you a link so you can share it with people. That's a nice way for people to hear. The whole thing. So that's a good idea.
Dr. Huang, how long will your talk be approximately?
35 minutes.
Oh, perfect. Excellent. So we have enough time to, to break the
Questions
ice
and-
and ask
yeah.
you interesting personal questions.
Yeah. I think, yeah, it's 8 o'clock. So
So are we good to go?
Yes.
we're good to go, JN?
Yeah, the Prakash starts.
Thank you so much. Thank you so much, all of you. Okay. Good morning, good afternoon, and good evening to all of you. Thank you very much for attending this wonderful occasion. Yeah. So we are very happy to have all of you here. So on behalf of the Center of Innovation in Mechanics for Design and Manufacturing, or CiMDM as we call it in short, yeah, of Texas A&M, we welcome all of you to this very special event. My name is Prakash Thamburaja, and I will be your host today. So before I turn it over to JN for some brief remarks and opening remarks, we humbly ask for all the participants to please turn off your cameras and microphones during this event to preserve bandwidth. Yeah. So we want to make sure that this event goes as seamless as possible. Okay. And it will go and with your work together, we will make sure that it happens that way. Yeah. So with regards to questions, if you do have any questions for our speaker or any of our panel members, please list them in the question and answer forum or in the chat forum as well. Yeah, it's up to you. So, preferably in the Q&A forum which we have. So I will pick the questions randomly. Okay. And if your question is selected, you may unmute your microphone and direct your questions to the speaker. Okay. So you can, this is a chance for you to let us know that you're there, and you can ask the questions to our speaker in person, at least through your voice. Yeah. Okay. Thank you very much. And I will hand it over to JN to give some opening remarks about our event today. Over to you, JN.
Yes. Well, very good day to all of you. And this is a second one in series of this type, JN Reddy Medal webinar. Typically, we present this in person at the annual conference of the Mechanics of Advanced Materials and Structures Journal Associated Conference, which we called ICMAMS, International Conference on Mechanics of Advanced Materials and Structures. But because of the COVID, we didn't want to delay in making these presentations very dynamic and global. So we are trying to reach out to everywhere, especially Far East and Europe and of course, United States. So I have the distinct pleasure this time, very close friend, very highly respected scholar, researcher, Professor Yonggang Huang from Northwestern University. He holds Jan Marcia Achenbach Professorship in Mechanical Engineering, Civil Engineering and Environmental Engineering, Material Science and Engineering, but his primary department is, of course, Mechanical Engineering. So I won't read his bio, but I think Prakash will take care of that a little bit in introducing Professor Huang. And I think you all know him very well. I mean, I don't have to say too much. He's a very highly cited researcher with many, many papers in Nature, Science. But he has, the title of the talk, as you can see, he's really working on very societally impactful problems with mechanics being focused from his side, and materials also at the center of this research. So Professor Yonggang Huang is selected to receive the 2022 JN Reddy Medal. So I'm very pleased to announce this publicly, even though it is known. So I want to let us give a good round of applause for Yonggang receiving this medal. So without further ado, let me return the operation back to Prakash to continue this.
Thank you. Thank you, JN.
I'll
Thank you
come
so
back
much.
at the end to say one more time, greet you and say goodbye.
Thank you so much, JN. It's very nice introduction. So just a bit about the JN REDDY Medal for those of you who are not familiar with it. So the description is as follows, yeah. The JN REDDY Medal was established in 2018 and is conferred in recognition of distinguished contributions to the field of mechanics of advanced materials and structures. Instituted by the Mechanics of Advanced Materials and Structures Journal, it honors JN Reddy, our good friend and well-known authority in applied and computational mechanics and founding editor-in-chief of MAMS Journal. And it commemorates his contributions as a researcher, teacher, and author of textbooks. As JN mentioned earlier, typically the JN Reddy Medal is conferred in person at the annual MAMS conferences, but because of COVID, we have to do it online. Yeah. So that is a brief description of the JN Reddy Medal. And I will also briefly describe our award winner today. There's a lot to mention, but we'll try to be as brief as possible. Yeah. So So Professor Yonggang Huang is the Jan and Marcia Achenbach Professor of Mechanical Engineering, Civil and Environmental Engineering, and Material Science and Engineering at Northwestern University. He is interested in mechanics of stretchable and flexible electronics and mechanically guided deterministic 3D assembly. He has published 2 books, 30 book chapters, and more than 670 journal papers, including papers in Science and Nature. He is a member of the U.S. National Academy of Engineering, U.S. National Academy of Sciences, a fellow of American Academy of Arts and Sciences, and a foreign member of the Chinese Academy of Sciences, the CAS. His research awards in the last decade include the Drucker Medal in 2013, the Nadai Medal in 2016, the Thurston Lecture Award in 2019, and honorary membership in 2021 from All American Society of ASME, the Praga Medal in 2017 from the SES, the Bazan Medal in 2018, the Von Karman Medal in 2019 from the ASCE, and he has also received the Guggenheim Fellowship from the John Simon Guggenheim Foundation in 2008. As Jan mentioned earlier, he's a highly cited researcher in engineering, material science, and physics as well. So he has also received multiple awards of teaching and undergraduate advising from the University of Arizona, University of Illinois and Urbana-Champaign, and Northwestern. And the 2022 JN Reddy Medal is conferred on to Professor Huang for being heavily cited for pioneering research on microscale plasticity and mechanics of stretchable electronics. Thank you so much. And Dr. Huang, would you like to say anything before we start your presentation?
Oh, thank you for this nice opportunity to present our work. I am really honored to receive the JN Medal, JN Reddy Medal. JN is really a great friend and great colleague, an inspiring figure in our field. So it's my great honor to accept this medal and to present this our work in his honor.
Thank you so much. Thank you so much, Dr. Huang. So before we start your presentation, is it okay if we ask some informal questions so that people, they probably know about you through your papers and your research, yeah? Because it's far-reaching, but it'll be a good chance for some of our audience members to know you as a person and as a friend as well, yeah? So is it okay if we ask you a couple of questions, informal questions?
Sure. Yeah, Prakash, before you start with the questions, Dr. Erasmo Carrera wanted to weigh in, and I'm going to let him talk for a second.
Sure, absolutely. Erasmo, yeah, please go ahead.
Dr. Carrera, you can now talk.
Thank you very much. So I think I cannot.
Yes, we can hear you.
Okay, so
Clear.
Thank you. Yeah, I'm pleased to to take the floor for a few seconds on that. I'm really happy that we are able to make this ceremony. Even though we are not able to make the conference, so that will be done next year in at your place. So of course I'm really happy as an editor of the journal, actual editor of the journal that has been funded by JN. Be part of the committee of this JN Reddy Medal, and we have really an outstanding winner this year. So I do congratulate Professor Huang once again, and we are all happy to have possibility to listen to your talk. So thank you very much.
Thank you. Thank you.
Thank you so much, Erasmo. Okay, so Dr. Huang, question 1. What are your hobbies?
Actually, the major one is actually to watch movies.
Okay.
This is really the one both all our family members enjoy.
All right, good. So that's a very nice hobby. Yeah. So at least it's something to do with and you can bond with your family members at the same time too. Yeah. So good. So question number 2. So what drives your research? Yeah. So what is your work and research philosophy? So what do you look for when you're actually coming up with problems to solve? Yeah.
The one what drives is the research is really fun. It's like a mystery solver, something mysteries and something mysterious. Then you go in, you explore, you find the answer. So this is it's really the most fun part. So it's not research is really not just to get more funding, to get more famous. It's really fun. It's a fun part. You solve some problem, and that's useful, and you find this is really fun.
That's a very nice answer, because this is something that I've always discussed with Arun as well, and actually we all we concur with your answer here. I think the fun part is what we address, which is the most fun part here. And one last question here. So since you won the JN REDDY medal, so what is your favorite memory with JN?
The part I remember vividly and very memorably is the conference at Texas A&M in 2014 or 2015, in celebration of JN's 70th birthday, where I meet all his family members, friends, and it was a great celebration. And over there, JN gave a very nice speech to talk about his life journey. That's a part I really enjoyed very much.
Oh, it's very nice. We are still waiting to celebrate his 75th birthday. Yeah? So I guess it's something that we have to keep on waiting. So, we have a lot of plans, but it's hopefully come to fruition sometime soon. Thank you very much, Dr. Huang, for such a very nice answer to these personal questions. Yeah? So without further ado, we would like to invite Dr. Yonggang Huang to present his talk today under the title of Modeling Programmable Drug Delivery in Bioelectronics with Electrochemical Actuation. Over to you, Dr. Huang.
Thank you.
Dr. Huang, we do have another personal question from the audience. How do you balance research and family life?
It's difficult. In fact, it's difficult. Family, of course, is most important, but doing research really also means a lot of sacrifice to the family, the time-wise and all these things. So I wouldn't say I have a good answer for that, but it's difficult to balance. And this may be a better question for JN.
All right, we'll talk about these. I did a little bit in a webinar some time ago. So let us, go forward with your lecture.
Thank you. Over to you, Dr. Huang.
Thank you. Are you able to see the screen?
Yes.
And I turn on a pointer. Can you see the pointer on the screen?
Yeah, we can see.
Okay, great. So the title of the talk is Modeling Programmable Drug Delivery in Bioelectronics with Electrochemical Actuation. And I like to emphasize this work is really in collaboration with my current PhD student, Roda Avila, and also my great collaborator, John Rogers. Without them, this work would not be possible. We all know the drug delivery system to some extent. For example, on the left, we show this is the seismic drug delivery system. The pills you take, the injection, and the patch. And we call them seismic delivery because those deliver drugs to your entire body. For example, the pills you digest, injection, the drug goes into your blood and goes through your entire system. Then some of it will be used to attack the disease. On the right side, this is called target delivery system. For example, the nasal spray, the inhaler. This is really try to solve problem locally. Locally, you have a problem with your nasal system, then use nasal spray. And each has its pros and cons, but in general, the target delivery is more useful, is more desired. For example, I want to say that here, when you deal with cancers, if you deal with a systemic approach, the cancer drugs really go through the entire body. It kills not only cancer cells, but also healthy cells. So if you can have cancer therapy that's really low, just go to the local desired sites. That'd be more effective in giving less pain and discomfort to the patient. So the purpose is to develop the drug target drug delivery system to deliver drug locally. And I'll use this example to illustrate this. This is the one of the new drug delivery system. It's using bioelectronics. This represents an emerging class of technology that can be used to stimulate for simulation in behavioral neuroscience. Basically, to deliver the drugs to the brain, you can see in the picture on the left, they put this device on the head of a little mouse, and this very big system delivered drug directly to the brain. The main, you can see in for the picture in the middle here, this one involves some needles that really insert into the brain of the mouse. And when it's triggered, it can deliver drugs. And such delivery system has some major challenge. For example, first, it's wired. So all this need to be wired, and it's really prevent the animal from moving around. And it's also battery operated. The battery takes a lot of volume. You can see it's a very large system as compared to the brain, as compared to the head of the mouse. And also, sometimes it's one-time use. You use it, then you have to throw it away. And it's only typically for one delivery, either deliver drug or deliver light or deliver electric signals. So a much better drug delivery system was developed by Professor John Rogers' group. And in this delivery system, as I'll show you in the picture next, it can really be implanted into the animal inside the body. And first of all, it's wireless. So therefore, it does not restrict the animal from moving around at all. Secondly, it's battery free. So the system is very small, it can be implemented or put in on the skin surface. It can do multiple drugs at the same time, and it's also refillable. This picture illustrates this drug delivery system. You can clearly see a cage, and outside the cage, there are antennas that deliver a strong electromagnetic field. And inside the cage, there's a mouse, and on the mouse, on its head, you can see it here. On its head, there's an NFC coil, near field communication coil. This coil can really harvest energy from the surrounding electromagnetic field and uses to power electric sensors and also the pumping system for drug delivery. So this is the picture. This is the mechanism for this drug delivery. Basically, if you see, let me go back to the previous. In this system here, I want to emphasize once the signal is given, then this NFC coil can receive the signal and use this to activate the drug delivery system. The energy of the drug delivery system really comes from the surrounding electromagnetic field, and that used to pump the drug into the body of the mouse. And this picture illustrates the pumping system. In the past, this flexible and stretchable electronic are used a lot, extensively as sensors. But this is a good example to show it can also be used as actuator to pump the drugs. So I use different colors to represent this different component in the system. On the bottom, you'll see the brown color, and that is the substrate to hold the system together. And then you see the yellow color. Those yellow colors are the electrodes. Okay, those are the electrodes. The blue one here is electrolyte. This is for chemical reaction. The purple one, those are the flexible membrane. And above that, the pink one, those are the drug. And further above is a green one, that's a reservoir. And above that is the microchannel. So basically in the system here, there are two reservoirs, two chambers. One is electrolyte chamber. That's for electrochemical reaction. One is the pink one, the drug chamber. That's a drug to be delivered. So how does the system work? How does the system work? Hold on. So once the electrical current is induced in those electrodes, then the electric current initiate the chemical reaction in the electrolyte. So those electrolytes and their chemical reaction generates bubbles, generate gas. They are either oxygen or hydrogen. With more and more gas generated, the pressure inside the electrolyte chamber increases. So they deform or push the purple membrane. This purple one is a membrane. So with more and more gas formed, the pressure inside the electrolyte chamber, represented by this P, is larger than the pressure in the drug chamber. So it deforms the purple flexible membrane. And this flexible membrane further pushes the drug into this microchannel and reach the delivered site. So basically, you initiate the current chemical reaction. Reactions produce gas. This increase the pressure, deform the membrane. Membrane pushes the drug. Drug goes out through the microchannel and finally deliver the drug. That's a process. So in this process here, our work is to develop a model that can be used for the precise volume and flow rate control of the drug. Okay, and in this approach here, when we establish this model, we realize that in this entire system, look at the picture, look at the system. Even though it looks pretty simple, they involve really a lot of parameters, specifically 12. With so many more than 12 parameters controlling system, it's very hard to do just experiments to see which parameter dominates, which one controls the system, and how to control the drug volume and delivery time. So we really like to develop an analytical model and finally reduce all the 12 parameters to 2. That's the key. So in the end, when this model is finished, we give you 2 parameters that controls, those are the combination of this 12 and this 2 parameter controls the entire drug delivery process. So the modeling part here, when you do the modeling here, when you do the analysis, when you do the microflow, all these things, you need really computers. You need computer simulation, including fluid mechanics, including the finite element analysis for solid part. So we put a label here. You see the computer. This means if you do the traditional modeling, you will need the computer simulation. But our goal here is eventually to come up with an analytical model. That model is so simple, it involves only 2 parameters that control the entire process. And in the end, the model is totally analytical, so you only need a simple calculator to calculate the drug delivery time, flow volume, and all those things, those relevant parameters. So let me first tell you what those 12 parameters are controlling the drug delivery process. First of all, environment pressure. Okay, environment. You deliver drug to the environment, and this is, for example, the site for the cancer, and this the local pressure is important. Second, we will deliver drug. It goes through a microchannel. The microchannel geometry is important. The cross section size A and B, and also the microchannel length L. For drug delivery, drug is a fluid, so fluid with viscosity, the drug viscosity matters here. What else? The membrane deforms. So membrane, the geometry, the thickness, the radius, the size that matters, and also membrane material property. The Young's modulus, Poisson's ratio, the stress strain curve matters here, because the membrane need to deform. And later on, we also deal with temperature, because the bubble is formed. So using the ideal gas law, the chamber temperature is important. And of course, the coil where the current goes through, the current is also a parameter. So there are really 12 parameters controlling the entire drug delivery process here. So we need to set up models. And first, for the deformation of the membrane. Sorry. For the deformation of the membrane, for this purple membrane, one side is the pressure in the drug chamber. The other side is a pressure due to the formation of the gas from electrochemical reaction. So this pressure difference, P minus P drag, is pressure difference causing the membrane to deform and leading to its volume. This volume V here, this symbol V, is the volume of the drug delivered. So that's very important. But basically, between volume V and the pressure difference, there's a relation. And this relation, it depends on the membrane thickness, depending on membrane radius, depending membrane size, and the elastic modulus, non-linear elastic property of the membrane. In general, this function Fv has to be determined by the finite element. Basically, you have a flat membrane, you apply pressure difference, then it bends and forms this membrane. So in general, this need to be calculated by the finite element method. But I would like to give you an example. When the deformation is very small, when the drug volume is very small, then you can really use a plate theory. Okay, this membrane deforms like a plate, and if it's a plate, the function of V here is linear proportion to the volume, and here you see the bending stiffness of the membrane. You see the radius to the 6th power of this membrane. And unfortunately, when you do this drug delivery, this delivery volume is huge. Just to give you an idea, typically, when the deformation is much smaller than the membrane thickness, you can use this formula. However, in real drug delivery, you see this experimental picture? You see this one, initially it's totally flat, but now it becomes a hemisphere. So the deformation is huge, and you cannot use this linear elastic plate theory anymore. You really have to use the finite deformation of the membrane as well as the nonlinear behavior of the membrane. So that one, typically one has to use finite element method involving the nonlinear stress strain curve, and one has to use computers. Next is for the drug delivery. For the drug delivery, it's a very simple model. And on one side is the drug pressure. On the other side is this environmental pressure, P0. So the difference, drug pressure minus environmental pressure, is using fluid mechanics is related to the viscosity, to the flow rate, and the size of the cross-section size. So combining two of them pressure together, we find this is the pressure in the chamber. That's also the gas pressure. This is the pressure due to the deformation, the purple part, that is the pressure due to the drug volume V to be delivered. This is really from the solid part. And this is the last part here that's related to the flow velocity. That is due to the fluid flow in the microchannel. So clearly we relate P to volume and this flow rate. But I want to focus here. In this formula here, this function FV still need to be determined by the finite element method. So now put this together. This is the formula we just derived. And now about the gas formation. Where does the pressure come from? From the gas. So we intend to use the ideal gas law, and we need to use this formula. PV, ideal gas law, PV is nRT. N is gas, the molar number of the gas. So this one from gas formation, there's a gas generation rate. N dot is rate is related to the current. In other words, the larger the current, the more gas is formed. And this F is the constant, it's a constant. So using this, you can integrate, you can find the gas generated is proportional to current and also time, how long you initiate this process. So substitute this into the ideal gas law, we end up one differential equation. In this equation here, V is the one to be solved. This is a function FV, which need to be determined from finite element analysis. And here is time. So this is really becomes in ODE for the drug volume. So in this equation here, I want to emphasize it involves many parameters such as the microchannel size, the drug viscosity, the microchannel length, the pressure, the initial pressure at the delivery site, and the temperature here, and here I is a current. So with this one, and to determine this function FV, then we certainly involve the membrane thickness, the membrane size, and the membrane elastic and the linear elastic property. So we want to do some analysis of this one. So this ODE involves already 12 parameters with some initial conditions. So in general, people naturally say, well, if it's ODE, you don't have analytical solution. You use numerical NDE such as Runa-Osgood method to solve this, to solve ODE, and you use finite element to solve this function FV. So this is totally numerical. For us, we want to make this completely analytical. So we want to use perturbation method to solve this ODE. I will tell you what the perturbation parameter is later on. And later, we don't want to use finite element. We really want to use a membrane theory. So in the end, the solution from our model is completely analytic. This is why we put a calculator here. You don't even need a computer. It's one line formula. So how do we do this? Well, first of all, we need to introduce normalized parameters. Time, that's very important. That's but we normalize. We put a star time t star here. So in this normalization of time, it involves temperature, involves current, involves the tensile stiffness of the membrane, and involves the radius of the membrane. We also normalize volume, which is to be solved. We call it V star, and we use R0 cube, where R0 is the radius of the membrane. We use R0 cube to normalize the volume. And also for the function FV, we also number it properly. After this normalization, then this ODE involving 12 parameters becomes a much simpler one. In this one here, every parameter has the superscript star. Star means it's already normalized. So V star is to be solved. T star is normalized at time. But all these 12 parameters now become 2, marked by the red color. One is M star, Once P0 start, I would let you know what they are. But the first important thing, 12 parameters now after proper normalization become 2. And what is this M star? Well, M star here involves many parameters involving more than 8 among the total 12, involving the drug viscosity, the microchannel length, microchannel size, temperature, the microchannel radius, Young's modulus, thickness of the membrane, and also current. So we call them microfluidic resistance because it involves the larger the microfluid resistance, the larger the M star. So without the microfluid resistance, this M star is 0, but it also involves the current. So in this parameter, you can see the current and microfluid resistance as well as temperature, they are combined together. They act together as one parameter to affect the drug delivery process. The second one is the initial environmental pressure P0. But that P0, after normalizing, we call them P0 star. So only M star and P0 star, these two non-dimensional parameters control the drug delivery process. So now this is very useful. Say we said there's 12 parameters, but now it's down to 2. There's two combination that controls the process. Now we want to solve this. Well, we find that in experiment, especially for the experimental data from Professor John Rogers' group, we find this M star is typically very small. It's not 0, but typically very small. But let's first neglect this term. If we neglect this term, neglect this M star, that means we neglect the micro channel resistance. So if the membrane is deformed, it takes time to deform it, but once it's deformed, it immediately goes through microchannel without resistance to deliver the drug. For this one, then this term it disappeared. So this equation becomes ODE becomes the algebra equation, becomes very simple. So if you go back to the dimensional term, it tells time in terms of its volume. And this is exactly the relation we want to find because in general, for drug delivery, we know how much volume we want to deliver. Because for example, for humans, it typically it's 120 microliters. It's a small volume. We know for human, we need roughly 100 microliters. So we know the volume. But using this formula, we can immediately figure out the drug delivery time. The only thing we don't know is this function FV. That depends, but that one we need to find an element to solve. But once we know this FV, then knowing the volume, then immediately we can solve. We know how much time it needs. And so with this one, so this is a very useful formula, but this is under the assumption we neglect the drug, the microchannel fluid resistance. So let me first do some analysis here. Without this microfluid resistance, this 12 parameters becomes degenerate to 8 because all those parameters involving microchannels won't show up. The environmental pressure P0, you show this here. The microchannel, the membrane geometry and the membrane material property, well, that shows up in this color, purple function, because it depends on membrane geometry and the membrane material property. The gas formation temperature T is here in the denominator, T is here. The coil antenna, I antenna is here, okay? So this already tells us something very useful. You want to reduce the time, certainly if you use a larger current. If you use a larger current, then you can reduce time because it's inverse proportional to current. Well, you may say, can we increase the temperature? Not much, because this temperature is the temperature inside the chamber. The chamber is on human body, and the temperature cannot be too high, otherwise your body gets burned. So temperature, you don't have too much control. So, and P0 is the delivery side pressure. This one, you don't have too much control either. So what you can really control is the current, but also the membrane thickness and material properties and radius. So those controlling FV, the purple one, and so it's controlling the current that can affect your temperature. So with this one, we really want to improve this model because the model showed neglect the microchannel fluid resistance. So remember that solution is for vanishing M star. Now M star is not 0 anymore, but it's small. So we can do perturbation. We introduce the linear term M star, and this T bar star is the perturbation term to be solved. This is to be solved. And you can keep doing it to introduce the square M star square term, cubic term. You can keep improving this and get full solution. But let's focus on this first perturbation term. If you do this, substituting to the ODE, you get your solution. The black one here is the solution without accounting for the microchannel resistance. And this purple term, that is the effect from microchannel fluid resistance. You see the volume, drug volume comes in, and this function G, that is the non-dimensional function of FV, that also comes in and P2 star. So now we get this solution, and this solution has a part. This is the purple one is due to fluid resistance in the microchannel, and this one here is the this part here is due to the deformation of the membrane. So together we can put them back into the dimensional form. And in the dimensional form, as I already mentioned, the first part here on the left is due to the deformation of the solid. It involves the current, involves the parameter affecting the membrane deformation. In the second part, the part on the back, that includes microchannel parameter, like its viscosity, the microchannel size, and the cross-section size and length, and the pressure P0 here. So together, these two terms gives the total time for drug delivery. And I really want to emphasize the drug delivery time is important. For example, you say, well, if you increase the current, that will reduce the first term to make the drug delivery faster. But this current does not show up at all in the microfluid term, resistant term. So this term will always be there. That's for fluid to go through the microchannel. It doesn't matter how much current you generate. You use a larger current, this term, this time is still there. This will not be affected. Also, increasing current is not always effective. It has other hindering effect. If the current too large, then the produced pressure too quickly locally can make the patient discomfort. So we really want to find the proper range of those parameters for the drug delivery. So when combine all of them together, you find a simple analytical form for this problem. The drug delivery time is given analytically in terms of the drug volume to be delivered. All the rest are simply the material and geometric parameters. But over here, the only thing to be solved is this function FV, how it deforms when how much volume it generates under certain pressure. So this one, in general, we need to use finite element method to calculate the relation between volume and pressure. But we really like to do better later on. But let me first to confirm this formula makes sense. So we compare the total numerical solution. What do I mean by total numerical? You solve the ODE numerically. You solve the function FV by the finite element. But we compare the total numerical solution with we call the semi-analytical. What is semi-analytical? Semi-analytical, which means we still solve the function FV using finite element, but we use perturbation method. Okay, using this is what we call semi-analytical. We use perturbation method to solve the ODE. You can see very good agreement. Okay, very good agreement between the two. So this built as a confidence. The model, this approach is correct. The only drawback now is we still need to use finite element to solve this, which takes time for different designs. You have to run each time. So we really want to you develop an analytical method. By the way, this shows the flow rate. Flow rate is important for the patient comfortness. If the flow is too large, then patient can really feel the pressure. But once again, you see the good agreement between numerical solution and the semi-analytical solutions. And this model also worked very well as compared. It's validated by the experiment. So those you show the experimental data and compare with the numerical or the semi-analytical solution. You can see the discrete data agrees very well with the numerical solution without any parameter fitting. So this now we have confidence in the numerical model. The only thing we want to solve is we want to get everything analytical. We don't want to use a computer at all. We just want to solve everything analytically, get the simplest formula. So that means we need to find the function FV. And traditionally, the way we find FV is to use finite element. And I'll show you how to avoid this. So this is a plate. When the plate deforms, the maximum deflection will become capital H. When the capital H is very small as compared to the thickness of the membrane, typically we say 1/4. If it is like 1/3 or 1/4 smaller, then the deformation is bending. Then we can use a pure bending theory. Then you can find analytical formula for the function F. When the magnitude of deformation with capital H is on the same order of capital A of the little h, or the thickness, that is the most difficult part. We really have to use finite element to solve this volume. But when the thickness become much smaller, or the other way, when the membrane deformation, the maximum deflection is much larger than the thickness, then this is really deformed like a membrane. In other words, the bending effect is negligible. This is really like a balloon. When it's like a balloon, the deformation is very much like a spherical shape. And this is the part, even though it's very complex, it's spherical shape, we can still find it analytically. So this is the part when the deformation is large enough, we can use the membrane theory. The bending can be neglected. And I will use this to illustrate. When this deforms, we use angle phi as a parameter to characterize the deformation. As angle phi changes, the thickness changes. The maximum deflection H changes. So we can figure out the height, that's the maximum deflection in terms of phi. We can figure out the volume. Okay, this is going to be in terms of phi. And then using the mechanics, we can also figure out the strength inside the membrane in terms of phi. And the only thing we need is the stress-strain relation. If you tell me the stress-strain relation, then using this equilibrium, we can figure out the pressure difference, basically the function. So in this part, it tells you, if you tell me the stress-strain relation, then I can use phi as a parameter. I can figure out the volume in terms of phi. I can also figure out the pressure in terms of phi, so I can get the parametric equation. So I use linear elastic deformation. Linear elastic to illustrate this. For example, when the deformation, when the material is purely linear elastic, you can see, by the way, you can see this deformation here. Initially flat, deform into a shallow sphere, the deeper sphere, entire final hemisphere. This is the experimental picture. For us, if the material is purely linear elastic, then we can figure out the pressure difference in terms of phi. Then we can figure out the volume in terms of this parameter phi. We can eliminate, this is really parametric equation. When we eliminate this, we can get the pressure difference in terms of, therefore we get the function V, okay? And we compare this with the finite element, you see very good agreement. So without any parameter fitting, we can get already analytical expression for this if material is linear elastic. But now material is really hyperelastic. It's not linear elastic for those materials, for example, PDMS. So for hyperelastic, we use the hyperelastic model here. I'll skip the details of the derivation, but basic to show for the Money-Riveling model, we can also get analytical expression of function F. And you can see agree very well with the finite element. Okay, the solid line is finite element, the dashed line is our membrane solution. You can see good agreement between the two. And this Money-Riveling is also for one type. What about any stress strain behavior, any hyperelastic behavior of the membrane? Well, the most general is called the Marlowe model. What is Marlowe? Marlowe model basically use the stress strain curve. It doesn't assume any functional form. You do the uniaxial test of the membrane material, you get the stress strain curve. This is the uniaxial stress strain curve of the membrane material. So based on this stress strain curve, the Marlowe model gives the energy density function. So this model here is really based on the uniaxial strength curve of the same material. And of course, you see good agreement because it's really fit the stress strain curve. Once you have this, using our model, we can also derive our function FV in terms of the uniaxial stress. So basically, if you tell me the uniaxial stress strain curve can be discrete data, then I can give you the function FV. And you can see the green line is the finite element. The dashed line here is membrane. You can see, again, good agreement between the two. So using all this one, I want to say we go back to this formula. The difference now is this function FV now is no longer a numerical solution. It's a simple analytical solution. And that you can use a calculator to calculate the entire drug delivery time. And this one shows all 12 parameters, the dependence on all 12 parameters. For example, the environment pressure is here, pressure and pressure. The temperature in the drug channel, in the membrane, in the electrolyte chamber, temperature is here. The current is here. And what are the parameters? The drug resistance here, viscosity, the microchannel size and the microchannel cross-section size, the length is here, and the membrane thickness and radius, and also membrane elastic property is through this function FV, but it's analytical. So now we compare our totally analytical solution. It's one-line formula with a numerical. You can see very good agreement with them without any parameter fitting. So we tried different materials. We tried to do different material for the membrane. One is a polymer called SIS. The other is polymer called SBS. This is the uniaxial stress strain curve. Remember, we told you we only need the uniaxial stress strain curve of the material. With this one, we can get our analytical solution. And the solid line is our analytical solution. The dot line here is numerical. Numerical means you solve ODE numerically, you solve FV by finite element. And analytical, and anything here is this from this one-line formula. You can see very good agreement between the two. So now we can use this analytical formula for the design of the drug delivery system. And we like to really apply to prevent, prevent death from opioid. And this is a major problem for the drug. And this shows the number of deaths due to this drug overdose in the United States. And you can see in 1999, there are some numbers, but in 10 years later, the number is really huge. Okay, the number of deaths reach 50,000 per year. So the idea here is to build a drug delivery system inside the human body. So later on, when it triggers that too much drug inside the human body, the patient basically faint. The blood oxygen level becomes too low, then automatically you don't need the human to inject this. Automatically, this one kicks in, the system can be activated to deliver the drug. And the drug to be delivered is on the order of a microliter on this order. For example, you can put this on abdomen, put the lower back, and put different part of the body. So we try to estimate the drug delivered for small animal like mouse is 1.5 microliter. For human, you need really 100 times larger, 120 microliter on that order. So we redesigned the system, designed the microchannel size, and all this are possible. And for example, using the current, for human, the current can be larger, like 10 microamp. So using this, you can find the microfluidic resistant, and using those one to design to estimate the drug delivery time. And typically, it's really important for once the person is in drug overdose, it's really important for the drug to be delivered within between 5 to 10 minutes and to save this person. So using our analytical formula, we can estimate for such a design how long it takes. Using this formula, we can find out how long it takes for this drug to be delivered successfully. And we tried different materials, SS polymers, SBS, linear elastic, and we find typically it's really 1 minute or 1 minute and a half using this design. So once this drug injection system is built in or implanted in the human body, if for the drug abusers, this can really save their life by kicking the drug automatically. So just concluding remarks, using mechanics model, you can really reduce 12 parameters controlling the drug delivery process into 2. And for this 2, using mechanics, you can find analytical formula using this analytical formula to design microchannel systems. With this, I'd like to stop now, and I'd like to thank Professor JN again. I'm really honored to receive the JN REDDY Medal. This is a great honor, and I hope this lecture shows how we use mechanics, apply mechanics for other non-mechanical systems such as drug delivery. Thank you very much.
Thank you so much, Dr. Huang. I think there are some questions. I think Dr. Raj Kota, I think he's able to ask on behalf of some of the people asking the questions. Yeah.
Yeah, I do have a raised hand from Vikram Deshpande, so I'm going to allow him to talk.
Please go ahead. Thank you, Raj.
Sorry. Hi, Yonggang. Wonderful talk. Can you hear me?
Yes, we can hear you.
The drive for the analytics, is it mainly to do with the fact that the designers of these materials, of these systems, will not want to do? Is this an engineering driver that's basically driving the sort of the analytical approaches rather than sort of numerical approaches?
Yeah, the main reason is once this formula is used, then those medical doctors or those electrical engineers, they don't have to rely on collaboration with mechanical engineer. They can really use this one and without really bugging the mechanicians to use this. So if in general, with this formula, sorry, let me show you the formula here. This formula for mechanicians, even without analytical formula, is good enough. I mean, you can do finite element relatively quickly for different designs. But over there, the issue is that people really want to try different materials. Therefore, for each different membrane, not just geometry, for each different materials, then you have to run finite element, do it again. But for medical doctors to use this, it's really best to give them something they don't have to consult a mechanician. It's much easier for them to use.
Thank you. It's wonderful engineering. It's superb. Thank you.
Thank you. Thank you for coming.
Any other questions?
We do have Dr. Srinivasa with a question. Dr. Srinivasa, you should be able to unmute yourself and maybe unmute. Yeah.
Thank you. Hi, Yonggang. It's a very interesting talk and a very nice point made on a number of items, which is very useful for those students who are listening also. Among other things, the importance of non-dimensionalization and getting a lot of parameters into a few. The question that I had was about the membrane model. So the membrane model that you have is treating this thing as a spherical cap. Is that right?
Yes, because if it's a membrane, then you basically bending. And
right. I get that.
Yeah.
I get that.
Yeah.
So for that's for inflation of a body because of pressure, there is a nice universal solution. That is true for all incompressible materials. This is one of Ericsson's 5 families of universal solutions for internal pressure. So, if you are interested, maybe you should look at that to see, because that may actually enable you to do this in a very nice way without having to even assume a Marlowe model.
Oh, very nice. Does that work for any materials, or you have some constraints on material behavior?
The only thing is it's an incompressible material. That's all.
Oh, I see. Okay. Very nice. I really look forward to this. I'll send you an email to get literature for that.
Please. This is actually one of the 5. This used to be something that people were doing a while ago. That is finding universal solutions, things that are valid for any isotropic material. And so this is one of the 5. And so there's an exact solution for it, even for a thick membrane.
Oh, very nice. Very nice. I'll definitely look into this.
Yes, please.
By the way,
I will send you the paper if this actually it's in Ogden's book also.
Great. Thank you for letting me know. I was not aware of that solution. Thank you very much.
So pure bending, spherical inflation, eversion, all of these things are universal solutions. So that's the reason you can just generate the solution without really any trouble.
Great. Thank you for letting me know.
You're welcome. Thank you.
I have a small question, Dr. Huang.
Yeah. Thank you. Go ahead.
So you might have talked about this, but in your calculations, does wall friction matter actually? Because since the geometries are quite small and the surface to volume ratios are getting larger, so will that affect your solutions? You might have talked about it, but I might have skipped it.
Oh! You are talking about the surface. Are you thinking about whether to account for the surface effect or not?
Yes, the friction of the fluid flow in the channels. Yeah.
Yeah, the friction in the fluid channel is already accounted for. Yeah, for this one, for the solid deformation part, the surface effect is not important at this scale. This really need to be pushed to the nanometer scale in order for that surface effect from solid part to be considered. For fluid, this fluid flow, if the resistance, that part is already accounted for.
The capillary effect.
I'm sorry?
Capillary effect.
Yeah.
Yes.
Thank you. Any other further questions from? Wait, let me see. There's some Q&A. That's Professor C.W. Lim. You have a question? You can unmute yourself.
Yeah, CW already asked the question about balancing the time.
No, but it's another one, JN. So just now only, just say, may I ask a question?
Sure.
There you are. Go ahead.
Shiva, can you hear? Or you can type the answer. Question. Looks like there is a connection problem or
Before that, there's is CW back on?
Yeah, Bala has a question.
Yeah, Dr. Balachandran has a question, Dr. Huang. He says, when would dynamics play a significant role in these applications?
Oh, yeah, very, very nice question. Not at this scale, because the delivery time is really on the order of several minutes. So the dynamic effect, the initial effect, is negligible in this analysis. But that's a very important point.
I think we're still waiting for. There's another.
Can you hear me now?
Yeah.
Yes. Go ahead.
Sorry. Thank you, Professor Huang, for an interesting talk, and I do enjoy your talk very much. I remember you mentioned about the that you do not have much control about temperature, because if it's too high, then our body cannot take it. But I'm wondering whether there's a lower limit for the temperature.
I cannot hear you well. Can you repeat the question again, please?
Yes, I remember you mentioned that you do not have much control over temperature T, because if it is too high, then our human body may not be able to take it. Is there a lower limit for the temperature?
Is there some limit for what?
Lower limit for the temperature.
Oh, I see. In this one, when this device is implanted inside the people or animal body, then there's very little control on temperature, because it's the same as the body temperature of human, right? So looking at the formula itself, we do not see a lower limit for T, as long as the ideal gas laws can be applied. But for practical use, temperature is not a good parameter to control, because it's just human body temperature. Does it answer your question?
Yes, thank you. My other question I might have missed in your talk. Do you consider non-Newtonian flow as well?
No. This is a simple model.
This
is a simple model. We have not account. Yeah. For fluid mechanics part, there will be room for improvement. We only take a simple fluid model.
Okay. Thank you very much.
Sure.
Dr. Huang, there's like a couple of questions here from Professor Debashish Roy from Indian Institute of Science. The first question: can the response of the scale non-linear ODE be scaled back to retrieve the original or true solution?
Can this be scaled back to what?
Can it be scaled back to retrieve the original or true solution?
Oh, I see. We have not done that. The reason is that we actually in this analysis we mentioned we want to do we go back to we also go to the second order perturbation. If you look at this one here, we not only did the first order, we also did m star square term, but over there we find for this microfluid channel, that term, the effect is not so important. It's negligible. It's much smaller. So we did not. Then we find the perturbation is good enough. We did not really go back to the original ODE anymore. But one thing I want to point out, this 2-parameter reduction, reducing from 12 parameters to 2 non-dimensional parameters, that is universal. Whether you solve the ODE or you use a perturbation or numerical, that the 2-parameter reduction is universal. It's just that using perturbation, we can get it analytically. I don't know whether this answers the question. Basically, we did not bother to go back to solve the original ODE, but we find for the interest of the drug, for our range of drug delivery system parameters, it's not necessary to solve the original ODE analytical anymore. Does this answer the question?
I'm not sure. I don't know whether Debashish is on, but he has another question which follows through is, are linearity and time invariance needed for scaling to not interfere with the nature of solution?
Can you repeat the question again?
Sure. Aren't linearity and time invariance needed for scaling to not interfere with the nature of solution?
Interfere with the nature of the solution.
Aren't linearity and time invariance needed for scaling to not interfere? Maybe if Debashish is on, he can explain his question in more detail. Debashish, are you on? I can see you're slowly coming up.
Yeah, am I audible?
Yes, perfect. Go ahead, Debashish.
Yeah, I was just wondering because for strictly nonlinear ODEs, if you scale, for example, this is very well known for chaotic solutions. You can't really scale it, right? So, for example, if something untoward were to happen, for instance, if there were to be a shock wave or something, then, something truly nonlinear, which cannot be mimicked by a strictly linear time invariant system were to happen in the response, then would scaling of this kind that you have used work?
Yeah, very good question. But I think that's related to the dynamic effect, right? I mean, this may be true if there's a shock of the injection, that could happen, but that's related to dynamic. For those kind of slow injection, typically happening between 5 and 10 minutes, or between 3 to 5 minutes, on the order of minutes, those dynamic effect is negligible. Therefore, I'm not sure the chaotic effect you mentioned is relevant here.
Yeah, I see. Okay, right.
Because injection is not a very fast process. It's not. If you inject, within minutes of time, those effects may not matter.
Yeah, that would perhaps also mean that there would be a linear system available, time homogeneous linear system corresponding to this nonlinear ODE, which would basically be able to mimic it.
Yeah, it's possible. It's possible. The major nonlinearity here really come from two forces. One is that the material becomes nonlinear. The second of all, even for linear elastic material, for example, even if the stress strain curve is purely linear elastic, but the deformation is very large. So geometric nonlinearity also comes in here.
Yeah, I understand. And thanks for a very nice talk.
Thank you.
Thank you, Debashish. And we have one final question from Jerry Chi. Jerry, would you like to unmute yourself and ask Dr. Huang your question? Because there are two parts to your question. I don't know which order you want me to ask. Yeah, go ahead, Jerry.
Hi, you got this talk. Actually, the second question being answered. I think I was also asking how sensitive, how fast we can control the delivery. So I just realized you're really looking at the slow drug delivery. So that's probably not the question. But how over this is sensitive to the viscosity of the drug?
Oh, viscosity of the drug. Actually, that the viscosity comes in here. Of course, this is a simple fluid model, but let me go back. Maybe I can find that formula.
But we do 3D printing, we deal with viscosity all the time. So I'm very sensitive.
The viscosity of the drug is really show up in this formula here. You see that there's a left part that's related to the deformation of the solid, and the fluid part that's related to deformation. That's a fluid flow. The viscosity only affects the fluid flow part. The larger the viscosity, the longer time it takes. But this does not affect the solid part or deformation of the membrane at all.
I see.
Just like viscosity affects the fluid part, the current affects the solid part, solid deformation. So this is two separate.
I see. So basically viscosity is separate from just control the fluid part. Okay.
Exactly.
Okay, great. Thank you. Very nice talk.
Thank you.
Thank you, Jerry. So with that, let's give Dr. Huang a big hand of applause, for a very nice talk.
Oh, thank you.
Thank you so much, Dr. Huang. And I would like to turn over the floor to JN to hear his closing remarks. JN?
Dr. Reddy, you're muted. Yeah, there.
Thank you, Yonggang, for a wonderful, very insightful lecture. So I think especially for those who are listening, whether near or far, young people, I think what the takeaway points are that doing some technologically impactful research, and especially societally impactful, such as the one that delivered by Professor Huang, I think is very important. We need to always think about what are the problems facing society or industry. So, at the very beginning of the lecture, one of the questions was related to research. And as Prakash pointed out, we talk about it and what really drives us, doing this research. It is the sheer passion, pleasure, satisfaction of doing things. But this satisfaction comes when the results are of some use, especially whether it is industry or in the case of this work, societally. I think even if it is an epsilon contribution, okay, very small contribution, but the pleasure that we take is enormous and it makes our day and makes us keep doing it. It's not the awards, honors, citations, all of these are secondary, but that sheer feeling of good of doing something that is beneficial to ourselves and the society we live in is very important. So I want to thank you, the audience, for logging in and listening to, and even if those people could not see it or listen, we will make this video available. So I also want to say that the 2023 JN Reddy Medal nominations are open now with a deadline of May 1st, 2023. The recipient will be recognized at the banquet of the conference, which is scheduled now from 9th to 11th of August, 2023. So this I sent with my reminder of this webinar today. So, but we will announce it regularly to larger audience. But please mark your calendar to be there. We will once again recognize the recipient of this year, Professor Yonggang Huang would be invited there. He would be recognized again physically. So with this, I want to close this webinar with a request to Yonggang to show if you have the medal in your hand.
Yes.
All right. So for some reason, because you have this, oh yeah, now we can see. All right. I don't know if that is me, but hey, I look like your brother. Yeah, if you look at closely, right? So thank you, Yonggang.
Thank you.
For showing this. So, all right. Lastly, I want to thank Prakash and his team, Raj, Arun, and of course Erasmo, all of you working in the background to make this webinar as successful as it is. And I'm very pleased to be here just to listen to my friend. And it's very interesting. This is still doing these analytical things. That is the part I still love. A lot of times students only think of finite elements or any numerical method, but there are problems that can be solved with simple analytical expressions. I mean, not everything, but there are. When you have that opportunity, we should do it. Because especially real-time computing for sensing and actuation of such as a drug delivery. We don't want this main computer to go do more complicated problem, but the improvement or return is very small. So that is where analytical solutions can really help. Even semi-analytical is better than full numerical. Thank you again. I look forward to seeing many of you at next year's conference.
Thank you, JN.
I think Dr. Srinivasa has something to add.
Seconding Dr. Reddy's point that, today, many times when we do finite elasticity classes and so on, people are not aware that there are a lot of exact solutions. So it's a good idea, and they're actually useful. So it's a good idea for people to kind of think about that also. And I'm glad that Yonggang brought that to the front. I mean, that's really quite nice.
Thank you.
And Yonggang, I sent you the papers on universal solutions.
Right.
So you can take a look at it. I'm hoping I sent it to the correct address. You can take a look at it, see if you can see if you can use it. That's all.
Thank you so much.
Yeah, you're welcome.
Okay,
well,
thank you so much.
Thank you to hear the voice of Vikram Deshpande, Devashish Roy, Balachandran, Jerry, and so.
Yes.
I mean, I'm sure there are a lot of other people who didn't ask. I know David Bigoni is online, but he didn't ask any question. So, and I'm sure Glausio is also there. So I don't want to name every one of them, but I know that you're all there. Thank you for logging in and make us celebrate this occasion with Yonggang.
Thank you
again.
Thank you.
Thank you so much, guys. So with that, we can close the 2022 JN Ready Medal presentation. And I wish you all a very good day and good night for those on my time zone, and happy working for the rest of you all, in this on stateside. Yeah.
Right. Thank you. Keep safe. And,
take care.
Bye-bye.
Bye-bye.
Thank you so much, Dr. Huang.
Thank
Take
you.
care, yeah?
Thank you so
Hope
much
to see
for
you when I'm in the
organizing.
US.
Thank you.
Take care.
Thank you, JN. Bye-bye.
Bye. Thank you, Prakash.
Thank you, JN. Take care. Yeah?
Yeah.
Thank you, Raj.
Thank you, Dr. Reddy. Yeah.
See you, Arun.
So, one minute before you get off.